Hello, Mechanics of Materials students. In this lecture, we'll look at the differential equations of equilibrium, which is our last extrapolation of state of stress at a point, where we're going to develop some expressions, some differential expressions for relating shear and normal stresses on a given element of volume of a body and related to forces that might be acting on that body, like gravity or maybe an electrostatic force that's pulling it around, but something that would be acting over an entire body. Gravity is the most typical one. So we'll start by just defining those body forces. So we'll say maybe we have body forces that can act in two directions, so gravity plus maybe something else. We'll call it maybe an electrostatic or a magnetic force that can pull something in another direction. So we'll define the total body force in the x direction as the force per unit volume in the x direction, little f sub x times delta v, the total volume, and then the same with the y. So big F is the force on the body due to body forces, not due to stresses acting on faces, is the per volume stress times the volume, and likewise for the y direction. And we'll take a look at a volume element that is a delta x, delta y, delta z, which will later shrink down into a dx, dy, dz. And for that, we're going to just take a look at a single section here, a single plane, a single z plane, a plane with a z normal coming out in the direction perpendicular to the screen. So we're going to define stress on the different faces, both normal and shear. And this time we're going to use our stress at a given point notation. And we're going to take note of the fact that this y0 plus delta y over 2 is indicating the particular location of these faces. So x0, y0 is the point at the center of the diagram. So this face, this whole face has basically a coordinate of y0 plus delta y over 2. This has a coordinate of y0 minus delta y over 2, and the same with x. And if we had a z-plane, we would be defining that the same way. If this were z0, the plane coming towards us would be z0 plus delta z over 2, and likewise going back. So we've defined our shears on our normals in terms of the face they're acting on, the direction they're pointing in, face they're acting on, direction they're pointing in, and then the location of that face with respect to a known coordinate point of an x0, y0 at the center. So I would just set this in static equilibrium, remembering that we have these body forces acting on them, as well as the net forces due to the shear and normal stresses acting on the faces. So if we tally everything up in the x direction, we of course have the capital Fx, which is our little body force per unit volume, times our delta v, our delta x, delta y, delta z. And if we tally up all of these stresses that have a component going in the x direction and then multiply them by the magnitude of, or the area of the faces that they're acting on, we can rearrange and we can get a sigma xx normal force in the x direction at the positive x face, at the negative x face going the other direction, same areas. We have tau acting on the y face in the positive x direction at the y location of the positive y face, and vice versa for the negative y. And if we take this is all equal to 0 for static equilibrium. So we have force 1, force 2, force 3, force 4, force 5. 5 forces. 1 body force and 4 forces due to either normal or shear stresses acting on those faces with those particular locations. if we rearrange this and we divide by the volume, because everything here has some portion of that volume contained within it, we're going to end up with, notice everything here is delta y, delta z, and here we have just some delta x, delta z. We end up getting basically three terms. Instead of our capital F sub x, we now have our body force per unit volume in the x direction. We have this set of terms that ends up being divided by delta x, and this set of terms that are divided by delta y. These are the normal forces in the x direction, and we notice that we have our reference x point plus delta x over 2, and then our reference x point minus delta x over 2. This is another way of saying the change in the normal force in the x direction on the x face with a change in x. y0 and z0 didn't change, and as we'll see on the next page, going from x sub 0, x0 plus delta x over 2 to x0 minus delta x over 2 is another way of saying x0 going to x0 plus delta x. And if we look at it that way, what we're setting up for here, if we took the limit of this term, we would end up getting the first derivative of our normal force in the x direction, sigma xx dx. And likewise with tau. We've got basically tau at one point, x0, y0 plus delta y being subtracted from tau at the other point at effectively y0 minus delta y, and then divided by delta y. So all of these three terms equal 0. So if we look at any function, we're gonna make the case that some x0 plus delta x over 2, and then that same x0 minus delta x over 2. This is pretty much, looking at the slope between those, this would equate to a basically function at one value minus function at the other value separated by a total distance of delta x. So basically this is the same as saying, you know, x0 here and x0 plus delta x here, and looking at the function value differences total separated by a delta x on our independent variable axis. So if we make that case, then this is the definition of derivative of first partial derivative of our normal force in the x direction with respect to x. So how much is that stress in the x direction on the x face changing as x changes? As we move in the x direction, how much does the sigma xx stress change? Moving back and forth. Same way with shear. The shear on the y face in the x direction, how much does tau xy change as we go up, as we change y? Does it get bigger? Does it get smaller? So we're looking at a rate of change, a spatial rate of change, not a time rate of change, of both normal and shear stresses. And if we include the body stress, our body stress per unit volume, we can make this relationship between some kind of body force per unit volume, the rate of change of our normal force in the x direction with respect to x, the rate of change of our shear stress, yx, which we know is equal to xy, with respect to y, all of that equals 0. So this is our differential equation of equilibrium, where F sub x is our per unit volume body stress in the x direction. We can do the same thing with y, make the same setup, and get a similar relationship. So in this case, our normal force or axial force is sigma yy. How much is it changing as we go up in y, increase y, and then the tau xy, the shear stress in the y direction on the x face, how much is it changing as x goes back and forth? We only looked at forces in the x and y direction. We could extrapolate this very easily to a case of forces in the z direction. We would just get the body force per unit volume going in the z direction, the rate of change of the normal force on the z face in the z direction with respect to z, and then the shear force in the z direction on the x face with respect to x, shear force in the z direction on the y face with respect to y. So we're seeing a pattern here. Body force in a given direction, rate of change of normal force pointed in that direction, in that face, with respect to that direction, and then the rate of change of the shear forces on a given face with the change in position of that face, basically. And one way to write this is in this indicial notation or our subscript notation, where we're for any body force in a direction I, we're going to add all of the different components, the different variations of our stress in the ji direction with respect to x sub I. So if j is 1, I is 1, x will be 1, then we'll have the shear components of, say, 1, 2, 1, 3, etc. So, for instance, if we say j equals 1 through 3, we can write this out as sigma 1i x1, sigma 2i x2, blah, blah, blah. So this would be a 3D version where if I is 1, here's the normal component, and then 2, 1, 3, 1 would be our shear components going in the same direction. And the important thing to remember is we're taking our partial derivatives of our shear components with respect to the change, with respect to the position of the face, not the direction. So this is looking at how the stresses change as we move in a given direction through the body. So we've looked at, so this kind of cinches our concept of stress at a point. We've looked at average stress. We've looked at shear and normal stress on a small area that we can define and for which we can resolve the vector. We've kind of looked at how shear and normal stresses change as we look at a given plane, a given small area in a body, and then rotate that with respect to the direction of applied stress and maybe an external coordinate system. Now we're looking at how the state of stress changes as we move the face of the volume element that we're considering away from a reference point. So we're looking at the rate of change of our stresses and relating those via, we still have to keep that volume element in static equilibrium. So say if this goes up, if our say our normal stress in the XX direction goes up with respect to x, these other three are going to have to, their combination is going to have to go down because everything has to equal 0. So now we're relating rates of change of shear and normal stresses and body forces in given directions with respect to changes in directions of the faces on which they're applied. So that's kind of our last look at ways that we can envision the state of stress with respect to a point. When is this valuable? It is most valuable when we have continuous functions that describe states of stress. That won't be all the time. A lot of times, though, we'll be able to estimate it. Obviously, things like a normal force that's due to pressure, we could describe that with respect to a given position, the change with respect to position via the weight of the column of fluid above it as a function of depth. We can do the same thing for any kind of fluid. We can look at this for various types of fluid resistance, shear, stress due to a fluid flowing over a given boundary. The friction will cause shear stress to be higher or lower as we go a certain distance away from that boundary. There's lots of examples of cases in which we'll have stresses that go up or down, that attenuate or magnify at a known rate in a given direction. So, and if we don't have a continuous function, in many cases we can develop one numerically. So, here's an example of one case where someone developed these relationships. Here's our relationships of normal force. So, our normal force in the x direction is a function of x, y, and z, increasing in each case. In the case of our normal force in the y direction, it's periodic in the x direction. So as we move in the x direction, our normal stress in the y direction varies sinusoidally, but it's linear as we go in the z direction. It's kind of like a sinusoidal wavy surface that gets bigger and bigger the further away we are in the z direction. And then just linear for z. The further away we get from our reference point, double that, here's our stress at any point. Shears are basically more complex functions of the same, not always positive. So somebody wants to know if we don't apply any body forces, there's no gravity, there's no nothing that's acting volumetrically. Given that set of functions, would a body be in static equilibrium? We got to assume it can assume any value of x, y, or z. So we have to apply, in that case, these general functions and say, we don't know where we are in the body, so the entire expression has to equal 0, so all points in the body are at equilibrium. So if we just crank through this, we would start by taking the first derivative with respect to x of sigma xx, with respect to y of sigma yy, and with respect to z of sigma zz. That's that first component of each of our conditions of equilibrium. So sigma xx, first derivative with respect to x, z is going to act like a constant and go away, and we'll just be left with y squared. We're going to take first partial of sigma yy with respect to y is going to equal 0 because there's no y components, and sigma zz with respect to z will just be 2. So here's the first part. Ooh. My mouse is failing me here. Okay, now we get to take the derivatives of the shears with respect to the face variable. So basically we're going to end up having to do these basically kind of twice. So we'll take sigma yx, which is the same as sigma xy, but we'll take it with respect first to y, then to x, because they'll be used in a different equilibrium expression. So first derivative of our shear on the y face in the x direction with respect to y is going to be this term as a constant, and we'll just get 4. We're going to end up having to take that derivative with respect to x for our y equilibrium, and in that case we'll end up with the 4y term as a constant, and we'll just end up with 3z. Likewise, continue with basically the mixed partials and get expressions for our derivatives for the shear expressions. Now we combine them. Basically, I like to go back to these formulas that we basically derived for equilibrium expressions in each direction. The normals are pretty easy, but I have to remember that I'm going to include my shears on the faces in the direction, in this case, of x. So I'm going to look for all my x direction shears. So I have these lined up correctly. So everything on this line is contributing to x equilibrium, and everything on this line is contributing to y equilibrium. Right? This is on the y face in the x direction, on the z face in the x direction. So I'm going to add all three together. And if I add y squared to 4, I get y squared plus 4, and this first partial of sigma zx with respect to z, derivative with respect to z of this term, we just get negative y squared plus 4. So if I add those, I get 0. So I don't need a little f of x to be in equilibrium. So this one says we have equilibrium in the x direction without the need for a body force. If I do the same thing with the y direction, I got 0 for my normal force, the gradient of my normal force in the y direction. If I look at the gradient of my shear force in the y direction, pointed in the y direction with respect to x, I get 3z, and then I have negative 3z coming from the shear on the y face, or excuse me, on the z face in the y direction. So again, no body force is needed there. But in the case of my z direction, I have 2 coming out of my normal force rate of change, and then I have 0 for both of the shears, which means I have a net sum of the forces in the z of 2. So I would have to add a negative 2 force units per unit volume of a body force to attain equilibrium. So that's the end of our rectangular differential equations of equilibrium. So again, a little bit esoteric derivation, but very simple. Define a volume element, look at the changes in position from a reference position at the center to the faces where we're applying the stresses, turn them into forces, group them, recognize that we have literally the definition of derivative in 2 instances, gather terms, and then basically apply them to each face. And again, we're looking at the rate of change of stress with a change in position of the face on which it's applied. Okay, let's do the same thing for a cylindrical volume element, because we have pipes and tubes and all kinds of things that are round in practice, and it would be nice to have a similar expression that we could use for cylindrical things. Spherical things are used too, but they're not as common. Pipes are easy to make, so we'll see a lot of the need for stress analysis of cylindrical type things, shafts and pipes. So we can define a cylindrical element, just cut one out here. This is a differential element, so we have a dr, d theta, at 2 different r's, and then a dz. And it's the 2 different r's that effectively create 2 different circumferences that make things a little bit complicated, as is the fact that we are not radially symmetric with respect to our tau theta r's. So we have a radially symmetric body where all of our stresses basically on the r theta stresses are going to all cancel out effectively when we start summing them all the way around. But we have opposite directions with nothing to balance when we go all the way around in the case of our taus. Again, they would be rectangular symmetric because we'd basically have something else, balancing them, although those aren't working over the same area. But because we're looking for radial symmetry, we can't really use that argument. So what we conclude, this is a little bit of a jump, we say, because the shear stresses aren't radially symmetric, but the part is, if we're going to have the part be in static equilibrium, those just kind of have to be zero, or we're going to end up with something being non-zero and we're going to end up accelerating. So this is very important for this derivation, as we conclude that for a part with radial symmetry, the tau theta r has to be zero. So the shear stress on the theta face in the r direction is zero. So this kind of slippage that would kind of deform the pipe outward, I guess, shear, is zero. So you can you can stretch the pipe in a hoop stretch. You can maybe slide it in the theta direction on an R face, but you can't go necessarily, well, actually you can't, because those two would be equal in the stress tensor. So pretty much everything's happening normal in this case. So I guess it can happen in the z direction. You can get zr, z theta, but not r theta. In fact, you can definitely get z theta, which is torsion. So symmetry of the stress tensor, theta r theta. If one's zero, the other's zero. So having concluded that, we're not doing anything parallel to these faces. We've just basically convinced ourselves that because that's true, this pretty much captures everything going on with respect to this volume element. And now we're looking at a slice of the volume element. Z is going back into the screen here. So we can define a sigma RR at this face, and this is at the R plus delta R, and a sigma RR at just the R face. We can define two sigma theta thetas, one at the plus theta and one at the minus theta. For convenience, we define this angle that's subtended by the two theta theta faces as 2 times delta theta, where a single delta theta is just this. And that makes everything a little bit easier. So we're going to have to define the areas that we're operating on as being a little bit different, because this inner area is a little bit smaller than the outer area, but the sigma theta theta areas are going to be the same. So if we look at the outer face out here, we can say that its area, if we include the delta z coming out of the screen, we're going to have 2 delta theta times r plus delta r times dz. So d theta dr dz, our d theta is effectively 2 d theta, which we've defined, the whole theta angle, and then instead of r we have r plus delta r, and then of course dz coming out, and then the inner face is just 2 delta theta times r delta z, and the side faces are just going to be delta r, so r, or r plus delta r minus r is just delta r, and then the z face coming out. So those are more rectangular. There's no curve to those ones. If we sum up, we're not going to deal with the z direction here, but if we just sum up all of the forces in the r direction, so pointing towards the center or away from the center in group terms, we're going to get a similar kind of situation that we did for rectangular, but with a few different terms. We're going to end up with this sine term, because we're going to be taking only one portion of this sigma theta theta, only that portion. And those of you who are familiar with the capstan equation from statics are going to be kind of looking at this and going, this is looking a little similar. It also makes use of this kind of radial symmetry. Okay, so we are ready to group terms. We're going to divide by the volume of this little element, which is delta r, 2 delta theta delta z, kind of an average volume element. Divide that out of everything. We're going to rearrange terms, and we're going to use the fact that because we're talking about an infinitesimally small element, we've got real small angles, and we're going to use the same small angle approximation that at real small arguments, sine theta is approximately equal to theta. So this ends up being just a theta or a delta theta in the sine term. And that allows us to group terms again, and we'll end up getting our r terms grouped times r, and then we're ending up with a spare couple of terms. So we don't get just a rate term. So if we take the limit as our delta v goes to 0, divide by our delta v, this will end up giving us our change in our stress in the radial direction as we go out further out in radius, bigger diameter pipe. But then we're going to have a non-differential term, just our sigma rr minus sigma theta theta divided by r, and that's all going to have to equal 0. We didn't include a body force in this case, so this is just the forces, equilibrium of forces due to stresses on the theta face and the r face. We aren't considering any kind of z theta shear or rz shear in this case. So this is normal force only in this situation, and we eliminated the in-plane shears with the argument that it didn't conform to the radial symmetry. So that was the only big assumption we had to make, and beyond that was just simply putting this little volume element into static equilibrium and then making some small angle assumptions, and then grouping. The real key part beyond that was grouping this whole condition of equilibrium expression such that we could recognize this term and say, aha, if I rearrange things, I can get something that looks an awful lot like the derivative of sigma rr with respect to r. And you'll find that that's very common to a lot of these equilibrium condition based derivations for stress and strain expressions, is you will rearrange things mathematically after writing a condition of equilibrium of a volume element and go, good heavens, that looks like the definition of derivative of something with respect to usually an orthogonal direction in the coordinate system you're looking at. So that concludes our discussion of differential equations of equilibrium. So we now have a way of expressing the rate of change of a stress, normal or shear, as we move in a direction orthogonally in our coordinate system through our part. So we can look beyond just what is the stress at this point, but how much is the stress changing as we go in that direction? And that becomes very, very important when we try to make design decisions of how big do we want to make the part in that direction if the stress keeps going up in that direction. That may not always be the smartest thing. So that's one practical thought that you could tuck away in terms of why you might want to know a differential equation of equilibrium for stresses. So we will use these in examples later. I don't have examples of them right now other than the one we already did for rectangular, but they'll be the basis of some future discussions. So this lecture concludes our discussions, our recorded lectures for the concept of stress. Future lectures will continue with definition of strain, and we'll basically march through the same considerations for strain. It's a little bit more complicated in that we will be having to relate the concept of deformation, elongation, shape change with the definition of strain and strain at a point. But we'll basically follow the same pattern that we did for stress. And once we've done that, we'll relate stress and strain together using the constants of elasticity and create the total Hooke's law expression. So then we can go back and forth from one to the other. So looking forward to those.